In this video, we are going to talk about Argand diagrams, polar coordinates, and then lastly, I'll talk about the de Moivres theorem. The Argand diagrams are a way of representing complex numbers. So for example, let's assume we have a complex number, which is z equals 4 plus 3i. How do you represent this on an Argand diagram? So we need to sketch the Argand diagram. Let us assume this is the Argand diagram. And on an Argand diagram, the horizontal axis is the real part of z, and then the vertical axis is the imaginary axis of z. So let's assume we are using a scale of 2 units on both sides. So let's consider this Argand diagram. So what we'll do is that you can see that with reference to this complex number, the real part of z is equal to 4, and then the imaginary part of z is equal to 3. So on the horizontal axis or on the real axis, we will plot 4, and then on the imaginary axis, we will plot 3. So this is 4 on the real axis, and then this is 3 on the imaginary axis. So they intersect somewhere here, and therefore this point is the point z equals 4 plus 3i. What if it was not 4 plus 3i? And let's assume that z is equal to minus 2 minus 7i. Let's plot minus 2 minus 7i. So minus 2 on the real axis, and then minus 7 on the imaginary axis. Here is minus 6, so minus 7 is somewhere here, and this is minus 2. And therefore, this is the point z equals minus 2 minus 7i. What if z was equal to 4 minus 5i? Where will this be on an Argand diagram? So we have 4 on the real axis, and then minus 5 on the imaginary axis. Minus 5 is somewhere here, and 4 is there. So this is the point z equals 4 minus 5i. What if z is equal to minus 2 plus 3i? Where will this be on an Argand diagram? So minus 2 on the real axis, and then 3i, that is 3 on the imaginary axis. So minus 2 is somewhere here, and 3 is over there. So the point will be somewhere here. So this is the point z equals minus 2 plus 3i. Let's talk about the polar coordinates of a complex number. In the previous example, we see that complex numbers were represented in the Cartesian form. A complex number can also be represented in the form r theta, where r theta is the coordinates of the complex number in polar form. Now, r is giving us the magnitude of the complex number, z. And then theta is also giving us the argument or the angle that it makes with the real axis. And in this case, it is represented as argument of z. So the complex number in terms of polar coordinates can be represented as r into brackets cos theta, which is the real part of the complex number in polar coordinates, plus I sin theta, which is the imaginary part of the complex number in polar coordinates. It's either the complex number is represented as r theta in this kind of bracket, or it is represented as z equals r into bracket cos theta plus I sin theta. Now, theta has a limit, and the limit of theta is between minus pi and then pi. So theta is greater than minus pi, but less than or equal to pi. And this form of theta is known as the principal argument. So having understood this, let us express a complex number z equals 2 root theta plus 2i in its polar form. Now, if it was Cartesian form, then the real part of the complex number is 2 root 3, and then the imaginary part is 2. Now, let's convert this into its polar form. So the first thing will be to find the magnitude of z. The first thing will be to find r, and then r is the magnitude of z. The way to find magnitude of complex number is r, which is equal to magnitude of z, is equal to the square root of the square of the real part, which is 2 root 3 squared, plus the square of the imaginary part, which is 2 squared. So this is equal to square root of 2 root 3 squared is 4 times 3, which is 12. Then plus 2 squared, which is 4. And then root 12 plus 4 is the same as root 16, which is equal to 4. And therefore, r is equal to 4. So we have found r. The next thing is to find theta, which is the argument of z. But we can only find theta if we sketch this complex number in its Cartesian form. So let's sketch the complex number. So this is the real axis of z, and this is the imaginary axis of z. So it is 2 root 3 on the real axis. So let's assume here is 2 root 3 and then 2 units on the imaginary axis, and here's 2 units. So they are going to intersect somewhere here. So this is z, which is equal to 2 root 3 plus 2i. So we can draw this line, and you see that it makes an angle theta with the real axis. And we can complete it as a triangle. Now, what is theta? You know that tan, using SOHCAHTOA, tan theta is equal to the opposite. And in this case, the opposite is 2 over the adjacent. And the adjacent is 2 root 3. So theta is equal to tan inverse of, this 1, 2, and this 2 can cancel. So it's going to be tan inverse of 1 over root 3. And then the tan inverse of 1 over root 3 is 30 degrees. So let me write it well. Theta is equal to tan inverse of 1 over root 3 is 30 degrees. Now, the next thing is to convert this 30 degrees in radians. And 30 degrees is the same as theta equals to pi over 6 radians, because we need to just multiply this by pi over 180 degrees. So if you multiply this by pi over 180 degrees, you get pi over 6. So having gotten theta, the value of the argument, then we will then come and put it in this equation to find z in polar form. So z can be expressed as r. In this case, r was 4, then times cos theta, and then theta is pi over 6, so cos pi over 6, then plus I sine theta, and in this case, theta is pi over 6, so plus I sine pi over 6. So this is this complex number in its polar form. We'll be able to convert it into its polar form. Z is equal to minus root 3 minus I. Convert this into polar form. So the first thing, we know that in polar form, a complex number is written as r into brackets cos theta plus I sine theta. So let's look for r. R is equal to the magnitude of z. And then this is equal to the square root of the square of the real part plus the square of the imaginary part. And this one is minus root 3 squared plus minus 1 squared. And this is equal to minus root 3 squared is 3. Then plus minus 1 squared is 1. So this is equal to square root of 4. And then the square root of 4 is 2. And therefore r is equal to 2. So we have found r. The next thing is to find theta. Remember that we said that theta is the argument of z. And so what is the argument of z? We can find the argument of z by first sketching this on a Cartesian plane. So in terms of Cartesian, we know that this is the imaginary axis of z. And then this side is the real axis of z. So it is minus 3 minus I. Let's assume here is minus root 3. And then let's assume that here is minus 1. So minus root 3 minus 1 minus I is going to fall somewhere here. So this is the point z equals minus root 3 minus I. So we need to draw a line. You can see that it makes this angle, which is theta, with reference to the real axis. So we can find the angle theta. You know that tan theta is equal to opposite over adjacent. The opposite in this case is 1. And then the adjacent is root 3. So it's going to be tan theta equals 1 over root 3. So theta is equal to tan inverse of 1 over root 3. And therefore, theta is equal to pi over 6. However, the angle falls here. So we need to measure all the way from this part to this angle. And therefore, we can find the total angle. And this is going to give us pi plus pi over 6. However, we are not going to use this as theta because if you add pi over 6 to pi, it is going to be greater than pi. And remember that we said that the principal argument, which is theta, must be greater than minus pi, but less than or equal to pi. So therefore, starting from the positive real axis to where the angle is, we would rather start from the positive real axis in the anti-clockwise direction. In the clockwise direction. And if it is the clockwise direction, then theta is going to be in the negatives. So instead of doing this, we are going to do this. You can see that the whole of this from this part to here is minus theta. And therefore, all we need to do is just to subtract theta from pi over 6. So at the end of the day, theta is equal to pi over 6 minus pi. And theta is equal to pi over 6 minus pi is equal to minus 5 pi over 6. So therefore, the complex number in its polar form is going to be z equals r. And we got r as 2. So it's going to be 2 times. Then cos theta. Cos theta is minus 5 pi over 6. Then plus I sine theta. I sine minus 5 pi over 6. So this is theta in polar coordinates. Nonetheless, we are not done. We are not done because you can see that there's still further simplification we can do. So z is equal to 2 times. Now, let's consider this. Cos minus a is equal to cos a because cos is an even function. However, sine minus a is equal to minus sine a, because sine is an odd function, and therefore this is equal to 2 cos 5/6 minus I sine into bracket 5/6. So it is 2 times into bracket cos 5/6 minus I sine into bracket 5/6. Let's assume z is equal to 1 minus root 3i. What is the value of z in terms of polar form? So we know that in polar form, z is represented as r into bracket cos theta plus I sine theta. So we need to find r. R is equal to the magnitude of z, which is equal to square root of the real part, which is 1 squared, then plus the square of the imaginary part minus root 3 squared. And this is equal to square root of 1 squared is 1, then plus minus root 3 squared is 3. And therefore, this is equal to square root of 4. And the square root of 4 is 2. And therefore, r is equal to 2. So having found the value of r, let's proceed to find theta. Theta is equal to the argument of z. And then to find the argument of z, we need to sketch theta on a Cartesian plane. So this is the real part of z, and then this is the imaginary part of z. So let's assume this is 1, and then let's assume on this axis, this part is minus root 3. So you can see that 1 minus root 3 is going to fall somewhere here. So this is z equal to 1 minus root 3i. So if we draw a line from the origin, you see that it makes this angle, which is theta, with the real axis. So tan theta is opposite over adjacent. So the opposite is root 3, and then the adjacent is 1. And therefore, theta is equal to tan inverse of, let me rewrite it again. So therefore, theta is equal to tan inverse of root 3 over 1, which is the same as root 3. Therefore, theta is equal to tan inverse of root 3 is 60 degrees. But we need to convert theta in pi radians. So all we just need to do is to multiply the 60 degrees by pi over 180. And therefore, theta is equal to pi over 3 in terms of radians. However, if we start measuring it from this side to this side, you will see that at the end of the day, theta is going to be more than positive pi. But we said that for the principal argument, let me write it here. For the principal argument, the value of theta should be greater than minus pi, but less than or equal to pi. So therefore, instead of starting it this way, we are rather going to start it this way. And if we start it in the clockwise direction, then we will attach negative to the value of the argument. Therefore, theta is equal to minus pi over 3 radians. Let's then write it in polar form. Let's write it in polar form. Therefore, z is equal to r is 2, then times cos theta, which is cos, into bracket minus pi over 3, then plus I sine theta, and theta is minus pi over 3. So remember that we have already established that cos into bracket minus A is equal to cos A, and sine into bracket minus A is equal to minus sine A. And therefore, Z is equal to 2 times cos into bracket pi over 3, then minus I sine into bracket pi over 3. Let's talk about the multiplication of complex numbers in polar form. Let's assume that we have a complex number, Z1, which is equal to R1 into bracket cos theta 1 plus I sine theta 1. And then we have the second one, which is Z2 equals R2 into bracket cos theta 2 plus I sine theta 2. What is Z1 times Z2? Z1, Z2. So it's equal to R1 into bracket cos theta 1 plus I sine theta 1. Then times R2, which is the second one, into bracket cos theta 2 plus I sine theta 2. So this is equal to R1 times R2, which is going to give us R1, R2. Then we'll distribute this over this. So it becomes, let me use a big bracket, cos theta 1, then times cos theta 2 plus I sine theta 2, then plus, which is I sine theta 1, then times into bracket cos theta 2 plus I sine theta 2. So let me close the big bracket. And this is equal to, so let me bring it down here. This is equal to R1, R2, and the big bracket. So here is cos theta 1, cos theta 2. So cos theta 1, cos theta 2. Then here is plus I, then cos theta 1 sine theta 2. And here is plus I, and here is cos theta 2 sine theta 1. Then plus, sorry, but you see that in the last part it's going to be I times I, which is I squared. And we've said that I squared is equal to minus 1. Therefore, here is going to be minus sine theta 1, then sine theta 2. So let's group like terms. So this is equal to R1, R2 into bracket. So you see that this one and this has not got any I. So it's going to be cos theta 1, cos theta 2, then minus sine theta 1, sine theta 2. And then here is plus into brackets cos theta 1 sine theta 2, then plus sine theta 1, which is this, cos theta 2, I, then bracket close. Now let's do this expansion. What is cos into bracket theta 1 plus theta 2? It's equal to cos theta 1 cos theta 2, then minus sine theta 1 sine theta 2. And let's also do sine into bracket theta 1 plus theta 2. This is equal to sine theta 1 cos theta 2 plus cos theta 1 sine theta 2. So you can see that this one is cos theta 1 cos theta 2 minus sine theta 1 sine theta 2. It is exactly this expansion, which is into bracket cos theta 1 plus theta 2. And you can see that here is cos theta 1 sine theta 2 and then plus sine theta 1 cos theta 2. So it's the same here. Here is sine theta 1 cos theta 2, which is this, plus cos theta 1 sine theta 2, which is this one. So all of this can be represented as cos into bracket theta 1 plus theta 2. And then all of this can also be represented as I sine into bracket theta 1 plus theta 2. So Z is equal to, Z1, Z2 is equal to R1, R2, big bracket, cos into bracket theta 1 plus theta 2, and plus I sine into bracket theta 1 plus theta 2. Let's assume that Z1 is equal to Z2 and this is equal to Z. So if it happens this case, it means that R1 is equal to R2, which is equal to R, and also theta 1 is equal to theta 2, which is equal to theta. So in other words, we are saying that Z is equal to R into bracket cos theta plus I sine theta, I sine theta times R, then cos theta plus I sine theta. What is the result of this? So you see that this is equal to R1, R2, which is going to be R times R, which will give us R squared. Then times, down here. So R times R is R squared. Then cos. The cos is theta 1 plus theta 2. In this case, it's going to be theta plus theta, which is going to give us 2 theta. Then plus I sine into bracket theta 1 plus theta 2. And this is theta plus theta, which is also going to give us 2 theta. So at the end of the day, I use this curly bracket. So at the end of the day, Z squared, because Z1 is equal to Z2, which is equal to Z. So in this case, we are looking for Z squared. So Z squared is equal to R squared into bracket cos 2 theta plus I sine 2 theta. Let's find Z cube. See that Z cube is equal to, we can write this as Z squared then times Z. So this is equal to R squared into bracket cos 2 theta plus I sine 2 theta. 2 theta. Then times R into bracket cos theta plus I sine theta. So using this same expansion, let's use it to write this. So this is equal to Z cube is equal to R1 times R2. R1 is R squared times R2, which is R. So here is going to give us R cube. Then into bracket cos into bracket theta 1 plus theta 2. So in this case, theta 1 is 2 theta. plus theta 2, which is theta. So it's going to give us 3 theta, then plus I sine into brackets theta 1 plus theta 2. And theta 1 in this case is 2 theta. Theta 2 is theta. So 2 theta plus theta is going to give us 3 theta. So you see that we are beginning to see a pattern. What is the pattern? The pattern is that z exponent n is equal to r exponent n, then into bracket cos n theta plus I sine into bracket n theta. This is a very important expansion, and it will lead us into a topic known as the Moivres theorem. Given that z1 is equal to into bracket 3, 0.7 and z2 is equal to 2, 1.2, find z1 times z2 and show that into bracket 1, 0 times z1 is equal to z1. Remember that we said a complex number z can be represented as r theta. So from here, that r is 3 and then theta is equal to 0.7. From the Moivres theorem, z exponent n is equal to r exponent n, n theta. So what it means is that if you are multiplying two complex numbers, multiply their radius and then add their angles. So in this case, z1 times z2 is equal to, into bracket, the first part is r exponent n, so which is going to be 3 times 2. So we multiply 3 times 2. Then this comma, then you add the angles, which is going to be 0.7 plus 1.2. And this is equal to 3 times 2 is 6. And then 0.7 plus 1.2 will give 1.9. Therefore, z1 times z2 is 6, 1.9. And it says that we should show that 10 times z1 is equal to z1. So let's write 10 then times z1. What is z1? z1 is 3, 0.7. So now this is equal to what we said earlier on. You multiply their radii, r. So it's going to give us 1 times 3, in another bracket 0 plus 0.7. This is equal to 1 times 3 is 3, 0 plus 0.7 is 0.7. However, remember that we already established that z1 from the question is 3, 0.7. I forgot this bracket. So this is equal to z1, exactly what the question asks us to show. For any complex number, into bracket r theta, show that into bracket 1 over r theta times r theta is equal to 1, 0, where r is greater than 0. So remember, using the Moivres theorem, z exponent n is equal to bracket r exponent n, n theta. So into bracket 1 over r theta times to bracket r theta is equal to, you multiply the r, so a big bracket 1 over r times r in one bracket, then comma, then you add, sorry, I made a mistake in the question, so here's minus theta, so therefore here's minus theta, so we will add the theta, so the theta part is going to be minus theta plus theta. So this is equal to this one can cancel. So we'll get 1 comma. Minus theta plus theta is 0. And that is exactly what we're asked to prove. If z is equal to minus root 3 minus I, using the Moivres theorem, compute z cubed. And to be able to compute z cubed, we need to first convert this z into polar form. So let's convert z equals minus root 3 minus I in polar form. So what we need to do is to first find r, which is equal to magnitude of z, and this is equal to square root of minus root 3 squared plus minus 1 squared. And this is equal to root of minus root 3 squared is 3 plus minus 1 squared is 1. And this is equal to root 4. And root 4 is equal to 2. And therefore, r is equal to 2. And let's go ahead and then sketch it on the real and imaginary axis. So this is the real part of z. This is the imaginary part of z. So it is minus root 3 minus I. So let's assume here is root 3. Let's assume that this place is minus 1. So minus root 3 minus I is this point. So z equals minus root 3 minus I. So if we draw a straight line to this point, and you can see that tan theta is equal to the opposite. The opposite is 1 over the adjacent. And the adjacent is root 3. Or theta is equal to tan inverse of 1 over root 3. And therefore, theta is equal to 30 degrees. But we need to convert this 30 degrees in terms of radians. So in terms of radian, we need to multiply this by pi over 180 degrees. And this is equal to pi over 6. However, the angle starts from here to this place. But because of the principal argument, remember that we established that the principal argument theta moves or is greater than minus pi, but less than or equal to pi. So if we add pi over 6 to pi, is greater than pi. And therefore, what we will do is that we start from this place. And that place will make theta equals pi over 6 minus pi. And this is equal to minus 5 pi over 6. So the complex number in polar form, z, is equal to r times cos theta plus I sine theta. So z is equal to r is 2. Then cos theta. Theta in this case is minus 5 pi over 6. Then plus I sine minus 5 pi over 6. So z is equal to 2 times into bracket cos minus 5 pi over 6 plus I sine into bracket minus 5 pi over 6. And therefore z is equal to 2 to bracket cos 5 pi over 6 minus I sine into bracket 5 pi over 6. Let's find z cubed. So z cubed is equal to, let me use this bracket, 2 then times cos 5 pi over 6 minus I sine 5 pi over 6. All of this exponent 3. So this is equal to, but remember that from the Moivres theorem, z exponent n is equal to r exponent n, then times cos n theta plus I sine into bracket n theta. So z cubed is equal to 2 exponent 3 and times cos. In this case, it's going to give us cos 2 times 5 pi over 6. Then minus I sine into bracket 2 times 5 pi over 6. So this is equal to 8 into bracket cos 5 pi over 2 and minus I sine into bracket 5 pi over 2. However, we can see that 5 pi over 2 is greater than pi, and therefore we need to convert 5 pi over 2 in a form where theta is greater than minus pi but less than or equal to pi. And we can do this by subtracting 2 pi from 5 pi over 2. So theta is equal to 5 pi over 2 minus 2 pi. And this is equal to pi over 2. So therefore, z cubed is equal to 8 times cos into bracket pi over 2 minus I sine into bracket pi over 2. But we know that cos pi over 2 is the same as cos 90, and cos 90 is 0. Then sine pi over 2 is the same as sine 90. Sine 90 is 1. So all of this will be reduced to z cubed equals 8 times 0 minus sine pi over 2 is 1. 1 times I is I. And this is equal to 8 minus 8i. So therefore, z cubed is equal to minus 8i. Prove that cos 3 theta is equal to cos cube theta minus 3 cos theta sine square theta. So from the math theorem, z exponent n is equal to r exponent n, then into bracket cos n theta plus I sine into bracket n theta. But the complex numbers in polar form, z exponent n is written as, but from polar form, z is equal to r into bracket cos theta plus I sine theta. So z exponent n is equal to r exponent n into bracket cos theta plus I sine theta all exponent n. So let's equate this z exponent n to this z exponent n. So this implies that r exponent n into bracket cos theta plus I sine theta exponent n is equal to r exponent n, this part, times cos to bracket n theta plus I sine to bracket n theta. So this r exponent n and r exponent n can cancel. So at the end of the day, we have cos theta plus I sine theta all exponent n is equal to into bracket cos to bracket n theta plus I sine into bracket n theta. So from here we can see that cos n theta plus I sine n theta is equal to cos theta plus I sine theta exponent n. So in other words, you just move n to the top. So cos 3 theta is equal to, is going to be into bracket cos theta plus here, which is I sine theta all exponent n, and n is 3 in this case. So let's go ahead and expand cos theta plus I sine theta exponent 3. So this is equal to, using Pascal's triangle. So using Pascal's theorem is going to give us the factors are going to be 1, 3, 3, 1. Equal to cos theta cubed, then plus 3, which is this first one, times cos square theta, then times I sine theta, then plus 3 again, times cos theta, then times into bracket I sine theta squared, plus into bracket I sine theta exponent 3. This is equal to cos cubed theta, then plus 3 cos squared theta, so 3i, because there's an I here, so 3i cos squared theta sine theta. Then you can see that here's I squared. I squared is minus 1 sine squared theta. So it's going to give us minus 3. Minus 3. I squared is minus 1. So minus 3 cos theta sine squared theta. Then this one is I exponent 3. It's the same as I squared times I. I will know that I squared is minus 1, so it's going to give us minus I. So this will give us minus I sine theta cubed. So this is equal to, grouping like terms, cos theta cubed, which is this, and this one has got no I, minus 3 cos theta sine squared theta, then plus into brackets. So we are going to write those with the I. Yes, 3 cos squared theta sine theta, then minus sine cube theta I. So if we compare the real part to the real part of this, you can see that cos 3 theta is equal to this part, which is cos theta cube minus 3 cos theta sine squared theta. And that is exactly what we're asked to prove. Using the Moivres theorem, prove that cos 5 theta is equal to cos theta exponent 5 minus 10 cos theta exponent 3 sine squared theta, then plus 5 cos theta sine theta exponent 4. A complex number, which is z, is written as r into bracket cos theta plus I sine theta. And then we've already shown from previous examples that cos n theta is equal to, into bracket, cos theta plus I sine theta exponent n. And therefore, cos 5 theta is equal to, into bracket, cos theta plus I sine theta exponent 5. So let's expand this. This is equal to, the coefficient is going to be 1, 5, 10, 10, 5, 1. In terms of the Pascal, because it's n exponent 5, so from Pascal's theorem, this is the coefficients we are going to use. So this is equal to cos theta exponent 5, then plus, the next coefficient is 5, times cos theta exponent 4, I sine theta, then plus, the next coefficient is 10, cos theta exponent 3, then I sine theta exponent 2, then plus the next coefficient, which is also 10, cos theta or cos squared theta, then I sine theta exponent 3. And the next coefficient is 5, which is 5 plus 5 cos theta, then times into bracket I sine theta exponent 4, then plus the last one, which is I sine theta exponent 5. So this is equal to, let's break this down, cos theta exponent 5, then plus 5I cos theta exponent 4, then sine theta. And you see that here is going to be I squared. I squared is minus 1, so it will give us minus 10 cos theta cubed, then sine squared theta. And here is I exponent 3. I exponent 3 is equal to minus I. So here is going to give us minus 10I cos squared theta, then sine theta cubed. And here is I exponent 4. I exponent 4 is plus 1. So this is going to give us plus 5 cos theta sine theta exponent 4. Then I exponent 5 is going to give us minus, is I, because I exponent 5 can be written as I squared times I squared times I. And I squared is minus 1 times minus 1 times I. So this is equal to I. Therefore, this is giving us plus I sine theta exponent 5. So at this point, let's group the like terms. So this is equal to cos theta exponent 5, then minus this, which is minus 10 cos cube theta sine squared theta. And we have this one, plus 5 cos theta sine theta exponent 4. So we are done with the real part. Let's write the imaginary part. So plus this one, which is 5 cos theta exponent 4 sine theta. And we also have this part, which is minus 10 cos squared theta sine cube theta. And the last one is this part, which is plus sine theta exponent 5 I. So you can see that from the question, this was given, this is a real part of the complex number. Therefore, we need to equate this real part to the real part of the answer. So therefore, cos 5 theta is equal to cos theta exponent 5 minus 10 cos theta exponent 3 sine squared theta plus 5 cos theta sine theta exponent 4. And this is exactly what we were asked to prove from the question.